All right, so here again, this is just the same thing what I just said. So here we have some kind of an object, and this is the weight, 3 whatevers, okay? And here we have this is empty, so it has a weight of 0. Then we submerge it, and look at the water was up to the top. So when you submerge it, some of this water is going to come out, right? So that amount of water that comes out, that's what I mean. That's the displaced water. And so this thing goes in it. It displaces the water. So the amount of water displaced, is just basically the volume of this thing, right? But here's the thing. So the weight here was 3. Then it goes in the water, and the reading is 1. That means that there has to be a force of 2 pushing it up. Well, what's the weight of the water displaced? 2. Okay, so there it is. That's the buoyant force. Okay, so when a body, this is called Archimedes' principle. When a body is completely or partially, I just described completely, but it also works for partially. When a body is completely or partially immersed in a fluid, this works for a gas too, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So just to repeat, the buoyant force, weight of the fluid displaced, mass is rho v, weight of the fluid displaced, okay, g is g, rho is the rho of the fluid displaced, and the volume of the fluid displaced is just the volume of the object submerged, right? So anyway, that's how it is. Now why does this thing even exist? Why is there a buoyant force? Well, remember what we learned, I think the very first day that we started working on this chapter. We learned that the pressure depends on depth only. So pressure equals the pressure on top plus rho GD, right? The pressure was dependent on the depth. So that means, when you go down, you increase your depth, the pressure increases. So there has to be a greater pressure here than here, right? And so this minus that is a net pressure, and that's what you call a buoyant force. So it's nothing new, it just results from this. But now we know how to calculate it in different ways. So that's kind of cool. Oh yeah, now I'm just going to just prove what I just said. Okay, so the pressure depends on depth. So the pressure is a function of depth. So pressure equals P0 plus rho GD. So it's linear in depth. Okay, so let's just prove it. That, I just told you that the buoyant force doesn't matter where the object is, right? As long as it's completely submerged. Let's prove it, just using this formula. Okay, let's say that we want the pressure at 2 meters minus the pressure. Okay, so we have some object, right? It's 1 meter. 1 meter, right? 1 meter, okay? So just these numbers I'm just making up, but it's true. So the delta D is 1 meter, right? So it's 1 meter from the top to the bottom. So let's say pressure at 2 meters minus pressure at 1 meter. We'll just plug in a formula, So this subtracts, and then you just put in a D, 2 meters minus 1 meter, and you get rho G 1 meter. Okay. Now let's say we go 10 meters down, or 11 meters down, whatever. So the pressure at 11 meters minus the pressure at 10 meters. Again, this cancels. You just put in here rho G 11 meters minus 10 meters. You get the same answer. No kidding. Okay, now let's go way down. Let's say we have the pressure at 100,001 meters minus the pressure at 100,000 meters. Again, this cancels. You just put in the different D's. Rho G 100,001 minus 100,000. And you get the same answer. Okay? So that's great. And that's what I explained earlier. So it doesn't matter where you are, as long as you're completely submerged, the buoyant force is exactly the same. All right, now we're going to just kind of go through some things. So Everybody, students, pause your video and figure this out. Okay, so if an object immersed in a fluid sinks, well, that means it's accelerating this way, right? So obviously this force has to be greater than that force. So what's the answer? Yeah, right? So the weight of the object has to be greater than the buoyant force. On the other, okay, oh, now, wait a second, you don't supposed to see that yet. Okay, now, I mean, here's the answer, but I got to prove it, right? So therefore, the density, by the way, I'm just being lazy here. When I put DISP, that stands for displaced, it really stands for displaced fluid, right? So if the buoyant force is less than the weight of the object, because the object is sinking, that means that the density of the fluid is less than the density of the object. Now, how in the world do you come up with that? Well, let's see. So basically what I'm saying is whether or not something sinks or floats or whatever depends on the density of the fluid and the density of the object. All right, prove it. Okay, so let's do this situation right here. So we have the buoyant force. Ooh, that's nice. Buoyant force is less than the weight of the object. Well, that means, okay, the buoyant force is the weight of the displaced, the weight of the displaced fluid. So that has to be less than the weight of the object. All right? Well, weight, okay, that means the weight, mg, of the displaced fluid is less than mg of the object. Okay, great. Now again, you know, density is mass over volume, so mass is density times volume. So now we're going to say, so therefore, let's just substitute. So rho v displaced fluid is less than rho v of object. Right? Now notice I get rid of the g's, right? I divide it up by the g's. Okay? So this is rho v displaced fluid. This is rho v object. Now, look, the object is submerged in the water. So isn't the volume of the object the same as the volume of the fluid displaced? Well, yeah. Okay. So therefore, we can get rid of the volumes because they're the same, and we can just say that the density of the displaced fluid has to be less than the density of the object. Ta-da! Okay? So again, whether or not something sinks or floats or whatnot has to do with the densities. If it sinks, the density of the object is bigger than the density of the displaced fluid. All right, how about this? If an object immersed in a fluid rises, well, then it's accelerating this way, so the net force is this way, so the buoyant force has to be greater than the weight. All right, well, what does that mean for the densities? Well, you can figure it out, right? So if this one, it sunk, so the density of the object was greater than the density of the fluid. This one, it rises, so sort of obvious, right? So you can do the same thing. Do the same thing, and you ought to really do it. So if the buoyant force is bigger than the weight of the object, then the density of the displaced fluid is greater than the density of the object, using the same logic. How about this? If an object immersed in a fluid has neutral buoyancy, that means that that force equals that force. The acceleration is 0. Well, I just gave it away, right? So this has to be the same as that. That's called neutral buoyancy. And how does that work? That means that the densities have to be the same, using the same logic. Okay, so many years ago, I think it was in Utah and Idaho or something, some students told me that there used to be this soda pop called Orbits. And it had these little spheres in it. And you could eat them, you know. And they were so they were edible, and they were neutrally buoyant, right? I mean, they're not going up, they're not going down, they're just sitting there. And so when you drank the soda pop, you drank these weird looking things, you know, these little tiny spheres, which I guess were flavorless or something. But so this is a situation that demonstrates this, right? So the buoyant force acting on those little spheres had to be equal to their weight. And so that means that they had to have the exact density of the soda pop. So anyway, there you go. All right. Here's a question for you. What will happen to a neutrally buoyant object if its mass is increased by 1%, but the volume doesn't change? So let me give you a big hint. There's your hint. So the mass increases by a little bit, but the volume doesn't change. What's going to happen? So everybody pause your video and figure out the answer. All right, you should have the answer by now. If the mass increases but the volume stays the same, that means that the density increases. If the density increases, that means you're not going to have neutral buoyancy anymore, right? You're not going to have neutral buoyancy anymore. And so if the density of the object gets larger, that means it's going to sink. All right. Consider 3 suspended objects in the figure. All 3 have the same size, but these 2 have the same mass, and this mass is greater than the mass of A and B. So compare the scale readings. So obviously this is a buoyant force question. So everybody pause your video and figure it out. Okay, so let's see. Everything has to do with densities, right? Well, sorry. The buoyant force has to do with the weight of the fluid displaced, right? So let's do it. Okay. Everybody agree? All right. So make sure you understand that. Okay. What we want to talk about now is floating. Floating. So here, I have some water. And here I have a little aluminum boat. And you can see it floats. Okay, it floats very nicely. Okay, now I'm going to make a lot of noise. So now I'm going to take that same piece of aluminum and I'm going to smash it as small as I can get it. Should be good enough. Now watch. Remember, same piece of aluminum, right? So the mass didn't change, the weight didn't change. Okay, it doesn't float, right? It does not float. Why doesn't it float? What changed? Well, so here's the picture. Here's the picture. So here it was initially. So what's different? You know, what's different? And here was when it was smashed. So what's different? Well, remember, the buoyant force depends on the weight of the fluid displaced. So look, this is displacing a lot of water, right? This is displacing a lot of water. So there's a so the buoyant force is equal to the weight. That's why it floats. It's neutrally buoyant. But when I smashed it, how much fluid does it displace now? Well, not very much, right? I mean, it doesn't displace a lot of water at all. So therefore, the buoyant force, which is the weight of the fluid displaced, is really small. Right? The weight didn't change, the buoyant force changed. So since the buoyant force decreased and this stayed the same, it sinks. All right. So let's discuss that even more. Okay. So for the boat, for the floating boat, the buoyant force was equal to the weight of the object, right? Yeah. Okay. And again, what's the buoyant force? So therefore, the buoyant force is the weight of the fluid displaced, right? So I can just say the weight of the fluid displaced equals the weight of the object. Great. That makes sense, right? So what does that say? Basically it says if you're floating, right, this is floating, the weight of the fluid displaced has to equal the weight of the object. Now, another way to say that is this. Floating objects displace their own weight in a fluid. That's important. Floating objects displace their own weight in a fluid. Okay, it's important, right? I'm trying to stress it. Floating objects displace their own weight in a fluid. So here is a blimp, right? The Goodyear blimp. Why is it so large? I mean, it's floating, but why is it so large? Because the weight of the air that it displaces is the weight of the object. So look, you know, the weight of the object is kind of big, right? Well, I don't know how big it is, but, you know, the weight of the object is, you know, a reasonable thing. But air doesn't have a lot of weight, agree? So in order in order for the buoyant force on this blimp to equal the weight of the blimp, you got to displace a lot of air. You know, you got to displace a lot of air. So the weight of the displaced air equals the weight of the blimp. So it has to displace a lot of air. Okay, so here's a question for you. A 10,000-ton ship must be built wide enough to displace blank tons of water. Okay, so remember, the weight of the fluid displaced equals the weight of the object. So pause your video and figure it out. Okay, we're back. Well, the weight of the fluid displaced equals the weight of the object. So if it has 10,000 tons, it has to displace 10,000 tons of water. It's as simple as that. All right, now we're going to do a homework problem. So everybody read that while I erase the board. Okay, a 15-kilogram solid gold, statue is being raised at constant speed from a sunken ship. Well, that kind of relates to Hawaii, right? What's the tension in the cable when the statue is completely immersed in seawater? Okay, here we go. Wow. Okay, so tension, right? So that's a force, so we probably want to draw a force diagram. So let's draw the force diagram. Well, first of all, what are the forces? There's the weight of the object, there's the tension of the cable, and when it's in the water, there's the buoyant force pointing up. So there's the force diagram. So weight of the object, right? 15 kilograms times 9.8 meters per second squared is 147 newtons. Then there's the tension of the cable, and there's a buoyant force. All right, we're pretty good at that. So we're trying to find the tension. So we know that the tension, okay, so the sum of the forces equals 0. Why? Because it's being raised at constant speed, right? Okay, sum of the forces is 0, so that equals tension plus buoyant force equals mg object. Therefore, the tension equals mg object minus the buoyant force. Okay, now let's do what we always do, you know. All right, so we got to figure out what the buoyant force is, right? Well, the buoyant force is the weight of the displaced fluid. So it's the weight of the displaced fluid, which equals mg displaced fluid. But again, you typically don't know what the mass of the water is, you know the volume. So it's equal to rho v displaced fluid. Might as well pull the g out, right? There. Okay. So that equals g rho displaced fluid times v displaced fluid. All right. Now, wait a second. What's the volume of the displaced fluid? It's the same thing as the volume of the object, right? Because the object is completely submerged. Okay, now, do we know the volume of the object? No, we don't. Can we find out? Can we figure it out? Yes, we can. Because we know the mass and we know the density of the gold statue. So that's good. So the density of the object equals the mass of the object divided by volume of the object. Therefore, volume object equals mass object divided by density object. Great! So we're making good progress. So therefore, let's keep going with this thing here. So therefore, the buoyant force equals G times rho displaced fluid times the volume of the object. And the volume of the object is this. So I'm just going to substitute mass object divided by rho object. There you go. All right. So now we can solve the problem. Okay, so go back here. So therefore, the tension equals the weight of the object. So the weight of the object is m object times g minus the buoyant force, which is this thing, minus g rho displaced fluid mass object all over rho object. And, you know, here we have a m object g. Here we have an m object g. Let's pull them out. We have an m object times g, 1 minus rho displaced fluid over rho object. And plug in the numbers. So the mass of the object, 15 kilograms. G is G. Then we have 1 minus rho displaced, 1.03, 1.03. Density of the gold, 19.3 times 10 to the third. So you do all that, and the answer comes out to be 139.1 newtons. So the buoyant force wasn't all that much, because look at, without the buoyant force, the tension would just be 15 times 9.8, which is 147, So including the buoyant force, the tension, it didn't decrease by much, like 8, right? Almost 8 newtons. But anyway, that's how you do it. This is a typical problem that you'll find in homework. This is your typical question in an exam. Just using the definition of the buoyant force, and you have to use, we use this all the time, right? Density is mass over volume. So make sure you understand that. That's a really good homework problem. Okay. Here's a question for you. Imagine holding 2 identical bricks under the water. Brick A is just beneath the surface of the water, while brick B is at a greater depth. The force needed to hold brick B in place is what compared to the force required to hold brick A in place? So pause your video and figure it out. All right, we're back. So what did we learn about buoyant force? It's independent of depth. So the answer is the same, right? The buoyant force is independent of depth. Okay, another question for you. Two identical glasses are filled to the same level with water. One of the two glasses has ice cubes floating in it. Which weighs more? Let me give you a hint. There's your hint. So, pause your video, figure it out. Okay, now we're back. So, the water with the ice cubes. The ice cubes are displacing some water, correct? And we know that the weight, well, it's this, right? Keep repeating myself. Floating objects displace their own weight in a fluid. So the ice cubes, the ice cubes are displacing water. And the weight of the ice cubes is the same as the weight of the fluid displaced. So therefore, the two have to weigh the same, right? They have to weigh the same. Because the water that's being displaced, the weight of that is the weight of the ice cubes. Okay, I hope you understand that. Let's do a similar one. Two cups are filled to the same level with water. One of the two cups has plastic balls floating in it. If the density of the balls is less than that of ice, which of the two cups weighs more? So pause your video and think about it. This is a really important question. You need to understand this. Okay, we're back. Okay, so instead of having ice cubes, we have plastic balls. Who cares? The plastic balls are displacing water, right? And the weight of the plastic balls has to be the weight of the displaced water. It doesn't matter what their density is. Okay, so it's the same thing. This is the same question as the previous one with the ice. Floating objects displace their own weight in a fluid. So make sure you understand that. This is from the book, but I thought it was kind of interesting. A manatee may look chubby, but these mammals live in fresh water and they have to dive for their food. Too much fat would make them positively buoyant, which would cost them energy to forage. A typical body fat percentage for a manatee is 7%. What? 7%? I wish I had 7%. Comparable to elite human athletes. And this reduces the energy cost for diving. Manatees, so that's incredible, right? They hardly have any fat. I mean, when you look at it, you think, well, anyway. Manatees have other adaptations to reduce their energy cost for moving in the water. They carefully adjust the amount of residual air in their lungs to achieve nearly neutral buoyancy. They can also move air from one lung to the other to roll, and for the top of the lungs to the bottom to tip forward for a dive. It's amazing. Amazing. Okay, so some people have a hard time floating in the ocean. I'm sure you know some people that have a hard time doing that. If you want to float in the ocean, what should you do? Well, you just got to reduce your density, right? How do you reduce your density? Just take a really, really big breath, right? Take a really deep breath, and it will reduce your density. Okay, that's a good place to quit. I think